So in the last segment, we saw an all pairs shortest path algorithm that ran in time order n cubed log n by repeatedly squaring something that looked like the adjacency matrix. This time we're going to show a dynamic programming algorithm, recall dynamic programming from a long time ago, that runs a little faster in time order n cubed. This algorithm was invented by two computer scientists, Robert Floyd and Stephen Warshall. So this algorithm of Floyd and Warshall will use intermediate vertices, much like the last algorithm, but it'll restrict the kind of intermediate vertices that are allowed in each subproblem. So basically what we're going to do is we're going to number the vertices of the graph from 1 to n in an arbitrary manner and define the following subproblem. Remember, dynamic programming thrives on solving subproblems of increasing difficulty until it solves the whole problem. So we're going to define the subproblem d superscript k of ij, I'm just going to call it dkij, to be the weight of the shortest path from vertex I to vertex j, where all the intermediate nodes have number less than or equal to k. Meaning you're not allowed to pass through any node whose number is greater than k, although the endpoints I and j themselves might be greater than k. That's not forbidden. So dk of ij is just for any pair of vertices I and j, the length of the weight of the shortest path that goes from I to j with all intermediate nodes numbered less than or equal to k. Now, if you follow this notation, then you realize that d to the n of ij is allowing you to have intermediate nodes numbered 1 through n, meaning any intermediate nodes at all. So d to the n of ij does not restrict the kind of path you can have from I to j. And so the smallest weight entry in d to the n ij is in fact the shortest path from I to j. And that's what we want to compute, d to the n of ij. So if you take the bottom-up view of dynamic programming, we're going to start with the small subproblems and work our way to the whole problem. What are the small subproblems here? So the base case of the smallest subproblems are d0 of ij. What's d0 of ij? The shortest path from I to j using no intermediate vertex, because every vertex is numbered between 1 and n, and we are allowed only intermediate vertices numbered 0 or less, meaning you cannot use any intermediate vertices at all. Now, do we know how to compute d to the 0 of ij? Yes, it's pretty easy. D to the 0 of ij is 0 if I equal to j, because if I equal to j, of course, as we've said many times, there is a path that has no 0 length that goes straight from I to I. It has weight 0, and it uses no intermediate vertices. So that path is acceptable, and d to the 0 of ij equals 0 if I equal to j. Otherwise, the only kinds of paths we can take which do not use any intermediate vertices are direct edges from one end to the other. So d to the 0 of ij equals the weight of ij if there is an edge from I to j. So that's a shortest path you can take straight from I to j with no intermediate vertices. Any other pair of vertices ij where there's no edge from the first to the second, you cannot get to without intermediate vertices. So d to the 0 of such ij's is infinity. So this d0s are easy to solve and write down. In fact, this d to the 0 of ij looks very much like the matrix A that we defined in the other algorithm for all pairs shortest path just in the last segment. So we've solved d to the 0s. So dynamic programming works its way bottom up and builds up the solution d to the 1 of ij, d to the 2 of ij for all ij, d to the 3 of ij, and so on. So supposing we've already found d to the k of ij for all ij. And now we want to find d to the k plus 1 of ij. If we can figure out how to do this, we can work our way to the top and get d to the n of ij. So given d to the k of ij, how do we compute d to the k plus 1 of ij? That's the question we will address here. So let's understand again the definition. D to the k of ij is the length, is the weight of the smallest weight path from I to j, which uses intermediate vertices numbered strictly between 1 and k. Sorry, including 1 and k. So it uses intermediate vertices numbered 1 through k. On the other hand, d to the k plus 1 of ij is the weight of the smallest weight path from I to j, which uses intermediate vertices all the way up to k plus 1. Now, what's the answer to this one? What is d to the k plus 1 of ij? Well, if you're allowing yourself intermediate vertices all the way up to k plus 1, there are two possibilities. Even though you allow me to go through k plus 1, it turns out that the shortest path from I to j still does not use any vertex numbered greater than k. So maybe all the vertices here, like this vertex here, has number less than or equal to k. That's possible. Well, we've already taken into account the weights of these kinds of paths, because d to the k of ij would have considered a path like this. So the only new paths we have to consider when we want to compute d to the k plus 1 of ij are paths that pass through the vertex k plus 1. For the moment, let's assume that all paths are going to be simple. We will actually show that negative weight cycles can be detected here also, so that we can tell for ourselves whether it was a good assumption to make that all paths are simple, all shortest paths are simple. But supposing a simple path is going to go from I to j through k plus 1. Because it's simple, it can go through k plus 1 only once. It'll never repeat the same vertex on the path, because simplicity means you go through any vertex at most once. Then if you look at this section of the path, what do we know about it? Well, all intermediate vertices in this section are numbered less than or equal to k. Similarly, if you look at this section of the path, again, all intermediate vertices are numbered less than or equal to k. Do we know the length of the shortest path from I to k plus 1, where all the intermediate vertices are numbered less than or equal to k? Yes, we do. That's exactly d superscript k of I k plus 1. Similarly, we know already the length of the shortest path from k plus 1 through j, whose intermediate vertices are less than or equal to k. And so we can actually compare, is the path going through k plus 1 from I to j shorter, or is the path not going through k plus 1 from I to j shorter? And that's exactly how the algorithm works. So if a path in d to the k plus 1 uses k plus 1, it goes through it only once, and all other nodes on the path are numbered less than or equal to k. So here is the key observation. This should be k plus 1. d to the k plus 1 of ij equals the minimum of d to the k of ij. This corresponds to the case where the shortest path from I to j does not go through k plus 1, or it does go through k plus 1, and in which case it's the shortest path from I to k plus 1, which only goes through intermediate vertices numbered less than or equal to k. It cannot go through k plus 1 because that would not be simple. And then the shortest path from k plus 1 through j, again going through vertices numbered less than or equal to k. So we're looking at the minimum over the two kinds of paths I showed in the last slide, and that's got to be d to the k plus 1 of ij. So now let's look at the running time of this algorithm. First, we have to, in dynamic programming, the way we analyze the running time is to say how many different sub-problems are being solved by the algorithm, and how long is it taking the algorithm to solve each of the sub-problems. In this case, each d superscript, I could call it k to be consistent, but it doesn't matter. It's a dummy variable. So each d to the I has n squared entries in it. It's an n by n matrix, so it has n squared entries in it. And there are n values of I. So we have n cubed sub-problems in all. We have to solve it for every possible superscript between 1 and n, and every possible pair of indices between 1 and n. So that's n cubed total problems. Now, how long does it take to solve any one problem, assuming you've solved the smaller ones already? So basically, once we've solved d to the k, if you recall how you compute d to the k plus 1 of ij, it just involves adding up two values from the previous superscript and then taking the minimum with respect to a third value. So all of that is just a constant number of operations, like just 2 or 3 operations. So it's order 1 to compute the answer to any sub-problem, and there are n cubed sub-problems. So the overall running time of this algorithm is order n cubed. And I hope you see how it fits the pattern of dynamic programming. And all along in the single source shortest path algorithm and the 2 all pair shortest path algorithms we've seen, we've used the optimal substructure property, which was also important in the world of dynamic programming. We've always said that in this case, for example, if you want to find the shortest path from I to j in the Floyd-Warshall algorithm, passing through the vertex k plus 1, we said, well, find the shortest path from I to k plus 1 and add it to the length of the shortest path from k plus 1 to j. We were able to do this because shortest paths have optimal substructure property. So think about that as you look at all the shortest path algorithms you've seen in the last few segments.